So now we know what a binary search tree is, right? We talked about the rules we apply to the tree, the fact that any parent that has children, the left child has to have a key value less than its parent, and any right child has to have a key value greater than its parent, right? Now let's talk about some of the operations we'll actually be performing on these trees and how they differ a little bit from our standard linked lists that we've talked about before. And the first thing I want to talk about is basically how we actually get around and traverse these trees, right? We go ahead, we could build up the tree, but how do we print it out and look at it and know that it's correct or not correct, perhaps even, right? Our normal linear traversals that we did in linked lists and stacks and queues aren't really going to work anymore because we have this whole idea of a node having more than one direction it could go, right? In our linked list, we just followed the next pointer, which took us to the next node. But now we have a left pointer and we have a right pointer. And if we take one of those paths in just a linear algorithm or just kind of a dumb loop, for example, we'll go down one path, but we'll never be able to come back up and get to the rest of our tree. Or at least not simply. You could do it, but the code is going to be very big and very ugly, which, isn't what we're going for here. So in order to get around that, what we have is this whole idea of in-order traversals, along with actually other types of traversals as well called pre-order and post-order. And you'll notice in a second why those are called in-order, pre-order, and post-order traversals. And basically, in order to traverse our tree correctly and simply, we're just going to implement a very simple recursive algorithm. And the basic idea is if we want to print out the contents of our tree in the correct order of the keys, then we're basically going to implement a very simple algorithm where the basic idea is the first thing we do is visit all of the left subtrees that we can. We go as far to the left side as we can, right? Which, if we go all the way to our left, that should get us to the smallest node in the tree. So we go all the way to the left, and once we get to the left, we go ahead and we print off the node we find. And after we print off the node, then we go ahead and we do the exact same thing with that node's right subtree. All right, so we're kind of following this whole idea of we dig down as far as we can go, we print off the node, we visit any subtrees of that node that exist, and then after we do that, we use recursion to come back up to where we came from before, and we just repeat this process over and over and over again, right? And I know that's hard to understand from just looking at these simple 3 lines of code here, well, 5, I guess, overall, with including the function. So the best way is to just visualize what's going on here, right? And as always, an in-order traversal is basically going to start at the root of our tree. So the first thing that's happening is we start at the root, right? That's the node we pass into our tree print in-order function. And if we look here, we can see the first thing we do is we basically descend into the left subtree as far as we can, right? So our first recursive call basically calls tree print in order node arrow left, which recursively calls B, right? So we get into here where the node value is B. We check to see if it's 0. If it's not, we hit our recursive call again, which brings us down to A. And then we make our final recursive call one more time. Right, after we have gone as far down the left subtree as we can, right, we see node was 0, so we return back, and then we do our next line of code, which is print the node off. After we print the node off, then we go ahead and try to visit the right subtree. So what happened here was we printed off the value of our current node, which was A. We printed that off, and then we tried to call print in order on the right subtree of A. And when we did that, nothing happened because the right subtree of A was null. There was nothing to do. So we just immediately returned back up our recursive chain, which is going to bring us back up to the recursive call that B started, which was initially kicked off by this call to our in-order function, and was just sitting there and waiting until we returned. But now that we have returned from that function, we will end up going ahead and printing off the current value of the node we're on, which is B, and then we'll do the same thing, but this time we're going to call our function on our right subtree, which brings us down to C. And if you can see what's going on here, we started by trying to recursively call our in-order print on our left subtree, but there is no left subtree right now, so nothing happened there. And then we went ahead, printed off our current value, which was C, and then we tried to make the same recursive call with our right subtree of our current node, which was null, right? So nothing happened there. After we finished printing with C, we've returned back up our recursive call, which brings us to B, which is now done, and brings us back up to D. And we follow the same process all over again, right? We printed off the current value of D, recurse down to the right subtree, and we follow the same process. Try to recurse left. There's no subtree to go into, so we try to recurse right. We printed off the value of E, and then tried to recurse right, but there is, again, no right subtree, which brought us back up to our root, and there was nothing else to do, so our in-order printing scheme completed successfully. And what you'll notice here is that our in-order prints actually printed off the value of the tree in ascending key order, right? So one very cool thing about binary search trees is we can really insert data randomly, but as we're building the tree, we're actually sorting it at the same time. So no matter what the state of the tree is or how many nodes we have in the tree, if we call an in-order search of the tree, basically we will get the contents of the tree printed back out to us in ascending order, right? And this is how you will really tell whether your tree is correctly built or not. If you call an in-order print or an in-order traversal of your tree and you don't get the numbers out in the correct ascending order, you know there's something wrong with your tree, okay? So beyond in order, we also have two other traversals we could do. We could do a post-order traversal, which is actually going to basically end up printing your tree in a descending order, or you could do a pre-order traversal as well, which just basically prints out the tree D to B, A, C, E, etc. But we'll look at those in other videos. Effectively, they are the exact same three algorithms. The only difference is basically going to be where you call your print node at. In a pre-order traversal, the print node is the very first thing you do. So you print off a node, then you go all the way to the left, you go all to the way to the right, and then you come back up. Whereas if we were doing a post-order traversal, the printing would be the very last thing you would do. So in a post-order traversal, you would recurse all the way to the left, then you would recurse all the way to the right, and then you would finally print off your node. Okay, it's just a matter of where you are doing your printing, which determines what kind of traversal you're doing. But we'll look at that in code in another video here in the future. So beyond just traversing the tree, we also kind of need to talk about, again, how we are searching the tree. Okay, so we can walk the tree. We touched briefly on searching, but thought we would just look at it again very quickly. It's pretty straightforward. So here, let's assume we are given some key that we're searching for in the tree, some directory entry. If you're looking for, Chad Mitzel in the DSU directory and the directory is stored as a binary search tree, you would use my last name as the key to search for, right? And just based on how the binary search tree is built, our searching is pretty straightforward, right? All we need to basically do is start at our root, the root of the tree, and we just check our current node against what the node is that we're actually looking for, right? So if this node happened to be what we were looking for, we would return, but it's not. And in order to determine where to go next or what to do next, we look to see whether the value we found is greater or is small, whether the thing we're looking for is greater than or smaller than the thing we found so far, right? So for instance, we were looking for, I guess in this case, they were looking for 66 at some point, so you compared 66 to our root, and because 66 is greater than our root, we traversed basically to our right child, which is 73. 66 is smaller than 73, so you traverse to the left, etc., and then you eventually find it, or you might not find it, right? Depending on whether the data is actually there or not. As you can see here, we just have some little pseudocode that does it. One thing I'll note is the pseudocode in the book for trees that you'll find in here for the most part are iterative, loop-based actions. The code I'm going to show you is going to be recursive, just because I think it maps better to trees and is actually easier to understand the recursive code than it is to understand some of the iterative code, just because of kind of the weirdness you have to go through to make this stuff work. Right, so that is searching. Pretty straightforward overall. The other thing to talk about is really, okay, so if we have a tree, we can search for an element in the tree, or we can, print everything off of the tree, but how do we go about inserting stuff into the tree? And inserting, too, is actually a pretty straightforward process. And all inserting basically accounts for is you give your algorithm the node you want to insert that has whatever key value that you're looking to put into the tree. And the first thing you do is basically just more or less do a search to see if that node already exists, or you're doing a search to figure out where that node should go. With the general idea being that if, for instance, let's say, just because I don't like how the animation works on this one, I'm just going to kind of do a little doodling here. Let's say, for instance, we want to insert the node 072 in here. Right, the first thing we're going to do is basically do a search for 72. All right, well, so the first thing we do is compare 58 to 72, and of course 72 is greater than 58, so we know 72 has to go on the right side of 58, but we can check and see whether 58 has any right children or not. And if it does not have any right children, then we know we can just go ahead and insert 72 on the right side. And we just do that by doing a simple pointer assignment, like we would do when we were adding a node to a linked list. You would just say left child equals our new node, right? Nothing too serious there, nothing you haven't done before. It's just in a different format. So besides adding that, let's say we would go one step further. And now let's say we want to add, let's go 60 to the tree. If we were adding 60 to the tree, we'd compare it to 58. Again, 58 is less than 60, so we know 60 has to go on the right side. So we traverse the right subtree. We would notice that we would do our comparison between 72. We know 72 is greater than 60, so we know 60 would have to go on the left side of 72. But before we would actually traverse down to the left child of 72, we would look to see if it has a child, which in this case 72 does not have a child. There's no node or no subtree to search beyond that point, so we would just go ahead and make our assignment there. Right, we would again just effectively say current node left child equals our new node. Right, that's all we're doing, is just simple pointer assignments there. Okay, so hopefully that looks pretty straightforward to you. Right, searching and inserting are all very straightforward operations in a binary search tree. Another thing to kind of be aware of as well is we kind of talked about what the height of the subtree is, or the overall height of a tree. All right, now the thing to remember is that the minimum height of the tree is effectively going to be log n of the total nodes, right? But that is only what we find in a best case scenario for a binary search tree. There are cases where the tree we get is actually going to be less than optimal. So, for instance, usually our most optimal trees for searching basically come when we start inserting data at random into the tree. If we just start inserting at random, we'll get a tree that might look something similar to this. And when we do that, you can see that our height of this current tree is 3. Now, this height is still going to be greater than what our optimal height would be, but that is just because of how the tree is structured. Now, if we would actually go about and insert an ordered list into our tree, what we're going to get is actually a fairly or exceptionally malformed tree with a height of 6. And remember, our worst case number of comparisons for searching and inserting and removing from a binary search tree is basically the height of the tree, right? So in this tree, the maximum number of comparisons that we would ever possibly have to do when we're searching for something is 3. Whereas in this tree, which is effectively just a linked list, it has deteriorated to the point where our maximum number of comparisons has become n, right? So no matter however big this tree / list gets, right, we're basically running at big O n time, in which case we just lose all of the benefits of our binary search tree, right? So usually inserting random numbers into a tree gives us a much better tree structure and brings us closer to the possibility of having our best case big O time. Now, this is, of course, a very obvious problem with binary search trees, something that's just inherent to them, but luckily we do have some solutions to these problems. And we'll see in a couple later videos here kind of how we address this whole idea of having this very unbalanced binary search tree, and how we can kind of restructure the tree as we go in order to make sure that we make that maximum packed tree that we were looking at before. So with that, that's really all I have in this video. If you have questions, make sure to get a hold of me and I'll get them answered for you.